Alan Aspect, John Clauser and Anton Zeilinger received the Nobel Prize in Physics this year 2022 for doing experiments with entangled photons and establishing the violation of Bell's inequality for entangled states and pioneering quantum information science. I will try to explain in this lecture what is quantum entanglement, Bell's inequality and some important quantum information science tasks pioneered by these Nobel laureates. The story starts from a paper by Albert Einstein and his collaborators. Einstein, Podolsky and Rosen in 1935 published a paper in Physical Review claiming that the description of nature provided by quantum mechanics is incomplete, where a more complete realistic theory with predetermined definite values of physical observables is possible. Actually, Einstein was not happy with the probabilistic interpretation of quantum mechanics. Using a pair of entangled particles, EPR proposed a thought experiment which describes a paradoxical consequence that does not fit with our common sense intuition. In the same year 1935, Erwin Schrödinger provided an additional paradox related to entanglement between a microscopic and a macroscopic system, and this paradox is also known as Schrödinger's cat paradox that describes quantum measurement problem. So, it is ironic that the sharpest attack on quantum mechanics came from these two great founding fathers of the theory. Let us start our discussion with the EPR paper, that is EPR paradox. The paper was published in 1935 in Physical Review. This is the reference, where we will talk about the David Bohm version of the EPR thought experiment. Before doing that, let us briefly discuss about entanglement and entangled states in quantum mechanics. Consider a composite quantum system consisting of two subsystems A and B. Quantum mechanics associates a Hilbert space HA for the subsystem A, and that we consider to be a spin half system, that is a two level quantum system. So, we consider this subsystem to be a spin half system, which is basically a two level quantum system, and HB is the Hilbert space for the subsystem B, which is also, we consider it to be a two level system, or we specifically we say it as a spin half quantum. Let ket up A and ket down A represent a complete orthonormal basis for this Hilbert space, this two level system Hilbert space, and ket up B and ket down B form a complete set of orthonormal basis for this Hilbert space HB. Here actually for this two level system or this spin half system, this up state and down state, these are the eigenstate of some spin operator. Actually here we consider it to be a spin component along z axis. So these two states up and down, they are the eigenstate of the spin operator. They are the eigenstate of the spin operator is z, that is equal to h bar by 2 sigma z. H bar is actually is equal to h by 2 pi. H is the Planck's constant. This spin operator is z acting on up state. So, when this operator acts on this up state, gives us the eigenvalue plus h bar by 2 and then the eigenstate, and Sz acting on the down state, down spin actually, gives us the eigenvalue minus h bar by 2 kate down. We see that the spin operator we have written here in terms of the Pauli spin operator sigma z. So, we can write down these eigenvalue equations in terms of this Pauli spin operator also. So, if we write the eigenvalue equation in terms of sigma z, then sigma z acting on the up state gives us plus 1 and then the state again, and sigma z acting on the down state gives us minus 1 down state. So, these eigenvalue equations are equivalent to this. So, this factor is there which we have to multiply with this plus 1 or minus 1 when we talk about the spin measurement. When we consider this whole system together, the quantum states and the operators for this joint system then will belong to a tensor product Hilbert space HA tensor product HB. In this larger Hilbert space, we can have a complete set of orthonormal basis vectors as this: of A tensor product of B, of A tensor product down B, and down A tensor product of B, and down A tensor product down B. So, because this is a two dimensional system, this is also two dimensional, the joint system will be 2 cross 2. So, 4 dimensional system. In this 4 dimensional Hilbert space, we can have 4 orthonormal bases in this way. This is one particular choice, but we can have a different set of orthonormal bases also. And we all know that in the quantum world, superposition of states are also valid quantum states. So, we can have superposition of these states also, they are also valid quantum state. So, one can also prepare superposition states for this composite system that belongs to this Hilbert space like this. So, we can actually have state for this composite system. So, we write down it here. One particular choice will be this one, up A down B plus down A up B, or 1 by root 2 up A down B minus down A up B, or 1 by root 2 up A up B plus down A down B, or 1 by root 2 up A up B minus down A down B. Here we note that we have actually dropped the tensor product symbol. Actually, we have to keep in mind there is a tensor product here, that is up A tensor product down B. This is actually down A tensor product up B. So, we have written this equivalently in this way: up A up B, this is equivalent to up A down B, and this is equivalently we have written there as down A up B, and this is down A, down B. So now this is a 2 cross 2 means 4 dimensional Hilbert space. So these 4 states they form a complete set of orthonormal bases for this Hilbert space, and we can have another set of choice. That means we can have also the superposition state. These 4 they are also orthogonal to each other, and these 4 states also can form a orthogonal basis for this Hilbert space. And for some historical reason, these states they are called Bell states or Bell bases. We cannot write any of these states as a factorized state like this. Some state psi of A tensor product, some state phi of B. So these states cannot be factorized in this way. They are actually entangled states, and which in fact are prepared in laboratory using, for example, photons, atoms and electrons. So we will discuss next the EPR paradox using this kind of entangled states. So after having some introduction about the entangled state in quantum mechanics, we get back to the Bohm version of the EPR thought experiment. So we consider here a pair of spin half particles A and B prepared somehow in an entangled state psi AB, where we have taken this psi AB as an entangled state. It is also called a singlet state, which is in a combination of up down, down up state. So this state was prepared somehow with through some interaction between these two particles, and then after that they were separated away. So particle A and B are freely moving in the opposite direction after this entangled state is prepared. Suppose Omlan has access to this particle A, that is this qubit. We used to call a 2-level quantum system as qubit. So Omlan has access to this particle A, and at a distance Bunty, say for example, has access to this particle B, and these two qubits A and B are correlated through this entangled state. And suppose Omlan measures qubit A by projecting onto this basis. So he is doing a measurement in this basis up and down. They are the eigenstate of sigma z. So he performs a measurement of spin along z axis. So they are the eigenstate of the spin measurement along z axis. So for this state, when Omlan performs the measurement in this sigma z basis, what he will obtain? He will obtain the result up, spin up for his particle with eigenvalue +1. So he will obtain the result spin up with the eigenvalue +1 with probability half, because the state is in this entangled state. So if he measures spin along z direction with probability half, he will obtain this state up with eigenvalue +1, and after the measurement the system will collapse to this part of the wave function. So after the measurement the system will collapse to this part of the wave function. So if he obtain +1 eigenvalue, that means if he obtain the up state after the measurement with probability half, when he obtain this on his particle, the joint state of the system will collapse to this part of the wave function. So this two particle wave function will collapse to this state up A down B with probability half, and with probability half he will obtain his state down with eigenvalue -1, and after the measurement if he obtains this down state for his particle, then the final wave function after the measurement will collapse to this part of the wave function for the joint system. So, for this result of Amlan's measurement, the joint state will collapse to down A, up B. Amlan can do this spin measurement, that is the sigma z measurement, using a inhomogeneous magnetic field, that is the Stern-Gerlach measurement. We all know that he will apply a magnetic field along inhomogeneous magnetic field along z direction. So, this up corresponds to this state and down will correspond to the down spin state. So, once Amlan obtained this result, spin up for his particle, then he immediately know that the joint state of this 2 qubit system is collapsed to this state, that is up A, down B. So, he can immediately predict about the state of the Bunty's particle. So, if Amlan obtain this result +1 corresponding to this spin measurement, then he can predict with certainty that Bunty will obtain the result -1 if he also measure spin on his particle along z direction, because of this consequence. Once Amlan's state is collapsed to this up state, the joint state collapsed to this up and down. So, from here, so at a distance he can actually predict with certainty that what is the state of Bunty's particle. So, if Bunty now measures also spin along z direction, then this he will obtain -1, that means spin down state he will obtain, and that Amlan can predict with certainty from here. Similarly, if Amlan obtain the down state, that is the -1 eigenvalue corresponding to the spin measurement, then he can predict with certainty that Bunty's state is in up state. So, if Bunty also measures spin along z direction, he will obtain the result +1, because the joint state after Amlan obtain this down state for his particle, the joint state for this whole system collapsed from this entangled state to this part of the wave function. So, in this part we can easily see that Amlan's particle is in this state and Bunty's particle is in up state. So, if he measures spin along z direction on his particle, he will obtain the result +1. So, Amlan can predict with certainty that Bunty will obtain the result +1 even if he is at a distance, because of this consequence of this wave function collapse. Consider now another case when Amlan decides to measure x component of spin instead of sigma z, that is this z instead of z component of spin. Now, he decides to measure x component of the spin, that is sigma x. Now, we note that the same entangled state psi a b can be expressed in terms of the eigenstate of sigma x. The eigenstates of sigma x are this up x and down x. Here I write x to indicate that these are the eigenstate of sigma x. So, when sigma x acts on this up x, we obtain the eigenvalue +1 and the same state eigenstate, and sigma x acting on down x will give us -1 down x. When we put a suffix x here, so that means these states are the eigenstates of sigma x, and here we have not given any suffix. So, these up and down, these states are the eigenstates of the sigma spin operator sigma z. Okay. And we know from as Sakurai quantum mechanics that actually this basis, that is this up x down x, this set of basis and this set of basis for sigma z, they So these also form a complete set of basis vector. These two also can form a complete set of basis vectors, and we know the transformation how to change the basis. We know that this up x and down x, they can be written. So these up x and down x states, these eigenstates can be written in terms of the up and down eigenstate of sigma z. And what is that? We remember from Sakurai quantum mechanics that up x is equal to, this can be written in terms of the superposition of those states up and down x is equal to 1 by root 2 up minus down. One can easily check that if we make this basis transformation, so we go from this up down state to this up x down x state through these transformations, then the same state can be written in this way. The same state can be written as minus 1 by root 2 up x a down x b minus down x a up x b. So the form of this state remains almost the same because of the symmetry of the state. There is only an overall phase factor here. So we will basically ignore this overall phase factor because it will not have any impact on the measurement statistics that we are considering here. The minus 1 is actually e to the power I pi, so it provides a phase factor here. So we will actually ignore that overall phase here. So basically now we can see after this basis transformation, this entangled state becomes this in the x basis, but the form of this state remains the same, that is in this form up down minus down up. So that one can easily check. Now for this sigma x spin measurement, suppose Omlan obtained the result plus 1, that is he obtained the spin on his particle, on his spin half particle as spin up with and that he will obtain with probability half, right. So following our previous argument we have just discussed. So once Omlan obtained the result up x on his qubit or on his spin half particle with eigenvalue plus 1, and that he will obtain with probability half because of this state. So once he obtained this result, that is this plus 1 eigenvalue, that means his spin is projected to this state, then the joint state of this whole system, that means system A and B, will collapse to this part of the wave function. So this after his result, after having this result, the joint state will collapse to this state up x a down x b. So we are following the same argument what we have already discussed for the sigma z measurement. Okay, and he will also obtain down x result with probability half because of this state, that means the result minus 1, and once Omlan obtained this result, that is down state with eigenvalue minus 1, the joint state of the system, the joint state of the composite system A and B will collapse to this part of the wave function. That means the joint state will collapse to down x up x b. So, following our previous argument, we can say that once Omlan obtained the result plus 1 for his sigma x measurement on his particle, then he can predict with certainty from here that Banti's particle is in this state, down x state. And now if Banti also measures sigma x on his particle, he will definitely obtain this result -1. And if Omlan, after doing measurement of sigma x on his particle, obtain the result -1, then he can predict with certainty from here that the Banti's particle will be in this state, that is up x state. So now if Banti also measures sigma x on his particle, he will definitely get the result +1. EPR then imposed their locality condition that since the two measurements are made at places remote from one another, one measurement is done on particle A, another one at a distance on particle B, the measurement outcomes of system B should be independent of what measurement we perform on system A. So, in other words, the measurement on system A should not influence the measurement results or outcomes obtained by system B. Then the EPR argument is the following. Since Omlan can predict in advance the result of measuring any chosen component of spin sigma x or sigma z on particle B by previously measuring the same component of spin on A, it follows that the results of any such measurement for particle B must actually be predetermined. That is, the values of sigma x or sigma z measurements were there whether we do any measurement on particle A or not. Because it is always possible for Omlan to predict the value of the measurement results recorded when Banti's qubit is measured in the same direction, there is an element of reality corresponding to that particular measurement observable, that is sigma x or sigma z. Now there is a contradiction here. These spin observables sigma z or sigma x, they do not commute. The observables sigma z and sigma x, they do not commute, means the commutator of sigma z and sigma x, we know that this is not equal to 0, this is equal to twice I sigma y. Now standard quantum mechanics merely tells us how to calculate the probabilities of these non-commutating observable measurements sigma z and sigma x when they are measured on system B, but standard quantum mechanics do not predict the definite outcomes of this sigma z and sigma x measurements. According to quantum mechanics, one cannot simultaneously assign a sharp definite value to these non-commutating observables, but in this case seemingly leads to a contradiction or a paradox here. So this was the conceptual puzzle presented in the EPR paper, and then they claimed that the standard quantum mechanics must have missed some fundamental elements of reality to present the predetermined values of non-commutating observables like sigma x and sigma z. In the next part of the lecture, we will see that nature does not respect the locality and reality conditions imposed by EPR when we discuss about Bell's inequality and the violation of Bell's inequality for quantum particles prepared in an entangled state.